Hi, this is Mr. Wilson with the Chapter 2 outline from Astronomy 100. Today we're going to be covering Discovering the Universe for Yourself, dealing with motions of the moon and the sun, seasons, daytime, and quite a few other topics that will get you into some of the activities we're going to be looking at on Tuesday. Our goals in this section are: what does the universe look like from Earth? Why do stars rise and set? And why do the constellations we see depend on latitude and time of year? What does the universe look like from Earth? Well, with the naked eye we can see about 2,000 stars, but that lighter band of gas and dust that you see going from upper left to lower right is the Milky Way galaxy. So that's something we'd be able to see on a clear night in an area that has very little light pollution. Certain parts of the sky, called regions, contain constellations, and for both the northern and the southern hemisphere we count about 88 different constellations that fill the sky, some of which you're going to be choosing for your second presentation. This is called the celestial sphere. This is a representation of all the stars and constellations and planets that might be out there observable in our nighttime sky. The line along which the planets and the sun and the moon appear to move is called the ecliptic, and that's a line along which at about a 23.5 degree angle it makes with the equator. So the sun, the planets, and the zodiac constellations pretty much line the ecliptic. So here's another way of showing you the celestial sphere. We'll look at another three-dimensional model of it in class. There's the north celestial pole, the south celestial pole, the celestial equator. So it's very similar to what you might consider an Earth-type mapping system. But all 88 constellations are somewhere on the celestial sphere. And somewhere in the night sky we can see this band of light that arcs across the sky. That, of course, is the Milky Way galaxy, the galaxy that our solar system is contained in. So the Milky Way galaxy is a collection of hundreds of billions of stars, and what we see of those blue arrows there would be our view from our position in the Milky Way galaxy. So when we look out and we see that band of light across the sky, we're actually looking toward the center of the Milky Way galaxy, along what's called the galactic plane. In our sky, we can identify objects by noting the object's altitude, in other words, how many degrees it is from the horizon, and the direction along the horizon, that being some sort of compass direction. The altitude, or the height above us, directly above us, is called the zenith. That would be an altitude of 90 degrees. And of course the horizon is 0 degrees. If we draw a north-south line across our field of view, that line is called a meridian. So for example, when the sun crosses the meridian, it's usually noon at our local spot. So we have the zenith, which is the point directly overhead, our horizon, which is pretty much the lowest extent that we can see, and the meridian, the line that passes across the sky from north to south. We can measure things in the sky, both the daytime and the nighttime sky, using angles, and we usually use degrees. So as you see in these diagrams, we can measure the angular size of different objects in the sky. A full circle is, of course, 360 degrees, but we can take 1/360th of a degree, that's 1 degree, and subdivide it. Those are called arc minutes. There are 60 minutes or 60 arc minutes in 1 degree. But even 1 minute is not a small enough measurement of what's in the sky, so we divide that into seconds. So 1 minute is equal to 60 arc seconds. So things that we look at in the nighttime sky, for example, are going to vary in distance. And of course, and the size of the object will vary in size as well. So we like to use these measurements of angular size, either degrees, arc minutes, or arc seconds, to measure the size of the distance. Of course, we know the Earth rotates, and as you can see in this diagram, it's rotating from west to east, or as seen from above the north celestial pole, in a counterclockwise direction. So if we were to leave a camera's lens open for several hours, we might see this photograph being recorded as you see on the right. The Earth rotates from west to east, so the stars appear to circle from east to west. And of course, the longer we keep the shutter open on the camera, the larger these arcs will be. So our view from Earth is basically limited by how far or how much above the horizon we can see. We can of course see the zenith directly above us, we can see the horizon, and we can see all the stars and objects in between. Any object that never sets below the horizon is called a circumpolar object. So as you can see, any red circle you see near the top of the diagram there would be a circumpolar star that never sets. And there are certain constellations that never set because they're always above the horizon. Those are of course called circumpolar constellations. We have a measuring system on Earth, and of course most of you know about it. It's called latitude and longitude. It's the basis upon which even our GPS systems on our phones and devices in cars work today. The latitude of an object on Earth is the position north or south of the equator, and the equator is defined as a line halfway between the North and the South Pole. So if we go south from the North Pole and north from the South Pole, we reach that line. That's the equator. Longitude is a bit different. Latitude's naturally defined, but longitude had to be defined by man in terms of lines going north and south across the globe. The first line of longitude was determined to be the prime meridian, and the prime meridian, even today, runs through Greenwich, England. So any longitudes that are west of the prime meridian are considered west longitudes. And of course, to the right would be east longitudes. So for example, Chicago is roughly at 42 degrees north latitude and about 93 degrees west longitude. So where those two lines intersect is of course our position on Earth. Well, the sky varies with latitude, but not longitude specifically. Latitude or altitude in the nighttime sky would be pretty easy for us to determine, but using longitude just really doesn't work very well. So there are other systems that we can use and we will learn about. As it turns out, though, there's one star which is very close to a point directly above the North Celestial Pole, and that star is, of course, Polaris. So if you're somewhere on the Earth's surface, let's say above the equator, you should be able to see Polaris at any time of the night. Unfortunately, the South Celestial Pole has no counterpart. There's no star at the South Celestial Pole. There are stars and constellations around it, but nothing at that point specifically. So the Northern Hemisphere has that one star which is very close to true north, or looking toward true north on the globe. This is a pretty important diagram that shows exactly the positions of various constellations. Those constellations being the basis of astrological predictions, not astronomical. So as it shows you, there are actually 13 zodiac constellations that are somewhere along the ecliptic The 12, of course, that most people know about as the zodiac constellations. But as you can see over on the right-hand side of the ecliptic, there's a 13th constellation which should be part of that set. It's called Ophiuchus. And unfortunately, for whatever reason, that was not included. But all the others, like Gemini and Taurus and Aries and Pisces, are all there. So when the sun appears to be in one of those constellations, it's apparently a very important day, or a series of days that people would believe certain things would happen favorably to them. But of course, at night, that constellation would not be visible. So looking in one direction, you're seeing the nighttime side. Up to the upper right, you're seeing the nighttime side of what the Earth would see. And looking toward the left, you see the sun, and of course the constellation that the sun is in. This is a kind of a strange comparison of two different ways in which we describe a day on Earth. You know, typically we think of a day as 24 hours, but in fact a day is a little less than that, about 23 hours and 56 minutes to make one complete rotation. To make one complete rotation and line up with, let's say, the sun, it takes another roughly 4 minutes. So there are two different kinds of days we can define: a solar day and a sidereal day. Now let's talk about the reasons for the seasons. First, what causes the seasons, and how does the orientation of our axis change with time? Let's skip that and go right to the season diagram. We see the Earth in 4 different positions as it's orbiting the sun. Over on the far left, we see the Earth with its axis pointing kind of in toward the sun, and over on the far right, the axis is pointing away from the sun. And the two in between are, of course, where the amount of sunlight reaching the Earth's surface is equal both day and night. Well, let's go back to the diagram on the Earth on the left. We see that most of the northern hemisphere is going to be lit up. Well, not only is it going to be lit up, there's going to be more hours of daylight. So the sun's light is more direct in that position, and we're receiving more sunlight, or more hours of sunlight, in that position. Of course, the opposite is true in December. So there's a direct relationship between where the Earth is in its orbit and the number of hours of daylight and the angle at which we're receiving that daylight. So what happens over a year's time? Well, the sun's altitude will change with the seasons. We know that in the wintertime, the sun is not only going to be lower in altitude at noon, it's also not going to be above the horizon as long as it might be in the summertime. And that's what this photograph is showing. It's a multiple exposure photograph showing the sun at different positions at different times of the year. The lower part of the figure 8 shows where the sun's position would be at noon in the wintertime, and of course the opposite in the upper left of the sun in the summertime. Well, you'd think it'd be a straight line, but it's not. As the Earth revolves around the sun, it changes speed very, very slightly, such that we'll see the sun at different positions in the daytime sky depending on the Earth's rotation and its position in orbit around the sun. So, Earth's axis points in the same direction all the time, but its orientation relative to the sun is going to change as it orbits the sun. Summer occurs in our hemisphere when the sunlight hits it more directly and we receive more daylight hours. Winter occurs when the sunlight is less direct. So it's the tilt of the axis that's really the key to the seasons. Distance is not. The distance from us to the sun is actually smaller in the winter time. January 3rd, I believe it is, we're actually closer to the sun in the northern hemisphere than on July 3rd. So it's just the opposite of what you would think. The distance itself might only be a 3% variation, but that is not enough to make a difference in the amount of heating we receive. It, again, is the effect of the axis being tilted. That's really what makes the difference in our seasons. So we mark 4 points that we consider important in our orbit around the Sun. The summer solstice, which is the Earth on the left side of the diagram, the winter solstice, which would be over on the right, and then the spring and fall equinoxes halfway in between. Equinox means equal night. So on those 2 particular days, March 21st, usually around September 22nd or September 23rd, is when we're going to receive equal night and equal day. So solstices and equinoxes can be actually plotted on our half of the celestial sphere, and you see them here in this diagram. The sun's path on the December solstice is the shortest and the lowest. The sun's path over on the left, the June solstice, is highest and longest across the daytime sky. This might represent a latitude of around 45 degrees latitude, very close to where we are in the Chicago area. Notice that the sun, no matter what day of the year it is, never reaches our zenith, never reaches a point directly overhead. It might be 70 or 72 degrees, but it's never 90 degrees. So that's something that a lot of people don't understand. We're just not at a latitude that would allow us to see the sun directly overhead. This is an interesting multiple exposure photograph of the sun at the Arctic Circle. Notice the sun never sets. Inside the Arctic Circle, on a day like June 21st, when the sun is at its highest in the northern hemisphere, the sun never sets. So at that particular latitude and higher toward the North Pole, you might experience 24 hours of daylight. But you can expect 24 hours of darkness in the middle of the winter solstice. So you're reaching some pretty extreme daylight hour lengths. Here's something else interesting about the Earth's axis. You would think that it's always pointing toward Polaris all the time. Well, in fact, it's not. In fact, right now it might be about a degree off from pointing directly at Polaris. The Earth spins like a top, and because it does that, it precesses. In other words, it wobbles. That wobbling causes the Earth's north axis to be pointing in different directions at different times. The total time it takes for the axis to, let's say, point in a circle takes about 26,000 years, I think the figure was. So right now we might be pointing toward Polaris, but in another 13,000 years, our Earth's north polar axis might be pointing toward the star Vega, as you see on the right. So there's a very, very big difference in where we take that north geographic pole and point it up into the sky. Now it's Polaris, but as time goes on, it'll be pointing toward different stars. All right, let's talk about the moon and the Earth and their relationships. Here's a section of the chapter that's pretty important, being able to realize what the phases of the moon are. And those phases are all because of our relationship with the Earth and the Sun. Sometimes the moon is going to be fully visible to us. Sometimes it's not going to be visible to us, in which we call it a new moon. And at other times, different portions of the moon's disk is lit up. It's always the same side that's facing us, but different amounts of it are lit. So these are the phases in the correct order, and I would expect you to be able to remember them, draw them, be able to identify them in some way. Going from the new moon, which would be no moon, there's the crescent phase, a first quarter phase, a gibbous phase, and then a full moon, and then another gibbous phase, a last quarter, and a crescent. Now the way to describe the difference between one crescent and the other, or one gibbous and the other, is by adding the word waxing. In other words, the amount of light that the moon is going to show us is increasing. Waxing is that word. So after a new moon, we'd call that a waxing crescent. And then first quarter, a waxing gibbous, and then a full moon, and then a waning gibbous. A last quarter, and a waning crescent. So waxing and waning are adjectives we use to describe the crescent and gibbous phases depending on where it is in the phase drawing. Something else interesting is the fact that we only see one side of the moon from Earth. And this is a good way to kind of model that. It's a good example. As the moon, this person moving around the Earth, goes around the Earth, if she did not change her orientation to the Earth, we would see all sides of the moon. But notice she has to rotate 90 degrees to keep her face toward the Earth. So the moon does rotate, and it rotates in such a way, it's called synchronous rotation. It rotates in such a way that we always see one side of the moon, and we'll talk about why in a different section. Now we need to talk about eclipses. The Earth and the Moon both cast shadows, just like any object in the sky that's exposed to sunlight. But when one of them passes through the other's shadow, that's what we call an eclipse. So how do we experience an eclipse? Well, the shadow is cast on something. The shadow might be cast on the moon, or the shadow might be cast on the Earth. And there are two kinds of shadows. One is called the penumbra, and the other is called the umbra. The umbra is the darker of the two shadows, and it's the one we'll concentrate on here. So this is how a lunar eclipse might work, with the sun, earth, moon in that order. So occasionally the Earth might block the moon's light. If the moon is moving across the Earth's shadow, the moon's light will be blocked. That's a lunar eclipse. But the lunar eclipse can only occur during a full moon phase. That would be when the light fully lights up the side we normally see. But there are three kinds of lunar eclipses. There's total eclipse, where the whole moon is blocked out except for the kind of the brownish shadow that the Earth casts. There could be a partial eclipse where the moon isn't completely covered by the Earth's umbra. And then there can be what's called a penumbral lunar eclipse, where the penumbra shadow of the Earth is cast, in which case there's very little change in the shade of or the amount of light reaching the moon. A solar eclipse would mean that the sun's light is being blocked as it's attempting to reach Earth. So notice what we have here. We have the sun over on the left, and the moon, and then the Earth. A solar eclipse would happen when the sun's light is being blocked. So solar eclipses can only occur during a new moon phase. So why don't we have an eclipse every new moon and full moon? Well, the moon orbits the Earth at a little bit of an angle, and that angle is enough so that the Earth, moon, and sun don't line up every time, every orbit, or every new moon, or every full moon. So that 5-degree difference between those lines or those orbits is enough so the moon doesn't line up exactly every time. So it must be a full moon for a lunar eclipse or a new moon for a solar eclipse. Got to have a new moon or a full moon phase. And the moon must be at or near one of the 2 points in its orbit where it crosses the ecliptic plane. If they're not lined up, there's no eclipse. We can actually predict eclipses. This is what's called a serocycle. So we can tell when not only the moon is in the right phase, but we can also tell when the nodes are lined up so that there will be an eclipse. And this is a good map of eclipses that will be occurring in the near future. There it looks like there's one coming up in 2017. That's in 2 years. Another one close to the Chicago area. Another one in 2024, possibly southern Illinois. But they occur all across the Earth at different angles and in different orientations. Some partial, some total, some just barely missing, depending on where you are on the Earth's surface. Well, last but not least is dealing with planets, and where ancient astronomers were able to see planets and try to figure out what was happening in the night sky. Basically, we can see these planets in the night sky at some point. Mercury, Venus, Mars, Jupiter, Saturn. Those are pretty much the closest planets to us, relatively speaking, and ones that we should be able to see at some point in their orbits. Of course, they're reflecting the light from the sun, so they'll have to be in a position such that they'll reflect the light and we'll be able to see it. But ancient astronomers had a hard time describing what was going on in the night sky because they would see something like this. They would see what's called apparent retrograde motion of planets. In other words, it appeared as if the planet was moving backwards for a short period of time and then moving back along its normal path. That was a very hard thing for astronomers to figure out, what was happening with this planet. To actually say that the planet looped in its orbit would be kind of hard to believe. But we can see it as something that happens pretty normally, as you see in this diagram, where one orbit passes the other, if you can say it that way. So, for example, Earth and Mars are shown here. And if we're looking at Mars in its orbit, at some points it appears to be moving backwards, and then it goes forward again, as you see in the numbered positions in that little tape strip in the night sky orientation. So there are times when we see planets doing this retrograde motion thing, and like I said before, it's something that ancient astronomers had a hard time trying to come up with a way of explaining it. So it's easy for us to explain because if the sun is at the center of the solar system and we're just one of many planets, then it's possible for one planet to lap the other. But it's very difficult to describe if Earth is at the center of the universe. In fact, pretty much impossible. So I think this is the last slide describing why the ancient Greeks rejected the real explanation for planetary motion. Well, they couldn't observe stellar parallax. They couldn't really see the difference in stars very, very far away and see if they shifted in the night sky. That would have told them that different stars are different distances from us. Astronomers at that time believed that all stars were the same distance from us, and that all of them would lie on this celestial sphere. And so that was a problem for the ancient astronomers. They just didn't have the technology to properly explain what was happening in the night sky.